to another special session of the seminar, actually. We generally have on Tuesdays, but we have a Francisco's guest here, and Francisco's going to do the introduction.
All right, thank you. So, hello everyone. So Harry, I met Harry probably 5 years ago while I was at Johns Hopkins. Harry worked with my advisor at that time, Ben Hobbs, while Ben was doing a sabbatical in Cambridge. Now Harry is an assistant professor at the School of Engineering, the University of Edinburgh in Scotland. We're right now working on risk-averse transmission and generation planning. Harry is here for a week and a half. So if you want to interact with him, you should take advantage of that. Right, go ahead, Harry.
Well, thank you for the introduction, and well, thank you for hosting me and for organizing this seminar. Just so I know who you are you all sort of electrical engineers or systems engineers?
I'm economist.
Economist?
I'm doing something in energy stuff, but
okay.
I'm not a technical guy.
I work in stochastic optimization.
So mathematics.
Yeah, apply to
Okay, okay. So this is the most difficult audience ever, because normally it's all engineers or it's all economists or it's all mathematicians. So I have a background in economics, and I work in engineering school and teach mathematics. So I'm somewhere in between, but I'm probably least well. Maybe I won't tell you what I think I'm least good at. So I look at economic problems in engineering systems using mathematics essentially. So Francisco emailed me, can you give me a title for this talk? And I was on a train and I had to think of something really quick. So I thought it might be nice if I just give you an overview of some of the things I'm doing and the sort of approaches I use. And then if you're interested, you can come and talk to me. And I'm here for the next week, and we can talk about that. So I decided to, as title, I decided to talk about energy systems modeling to inform policy. I don't like having modeling in the title of anything. I'll explain that later. But so the focus will be on how you can use models to do something useful. Do I have a remote, or do I just have to come back? Okay. But before I start, I'll tell you a little bit about where I'm from. So this is Edinburgh. Has anyone ever been to Edinburgh? No? You're missing out. So this is the old town of Edinburgh, which is parts of it are medieval and parts of it are a bit older. There's a huge mountain in the middle. Well, huge mountain in the middle. I shouldn't say this here, but there's by European standards, there's a mountain in the middle, which is probably about 300 meters high, which is one end of an old volcano, and then there's the other, and then there's basically a ridge there, and the castle, which you can't see on another end of the same volcano. Main university buildings here, the dome that you see. It's a very nice city. The weather is about the same as it is here now, even though it's actually summer in Edinburgh. But it's not that bad, and it's a very nice city to live in. It's a very nice city to visit as well, especially in August when there's a huge festival on, and there's thousands of shows every day. So if you want to come to Edinburgh, let me know. So there's lots of people working in, and of course Edinburgh is in Scotland, and the renewable resources are very good in Scotland. Scotland generates about 25% of its electricity from renewables, compared to a UK average of something like 10%. So Scotland generates most of the renewables for the whole of the UK, and has one of the highest rates in Europe. So not surprisingly, there's lots of people working on energy. Scotland also has transmission problems. There are transmission constraints between Scotland and England, where most of the demand is. So there's people working on that as well, but it's especially the renewable sector that drives that. So there's so University of Edinburgh is very big, especially compared to this university. So we have about 30,000 students, and engineering is the biggest school. But there's in the whole university there's about 150 people that I've discovered who do something with energy, and we're trying to integrate all that research into one sort of energy center. We're still working on that. So engineering is the largest concentration, and within engineering I work on something called the Institute for Energy Systems, which has about 26 people working, doing research, academic staff, so assistant professors and up working on energy, and lots of students. And we do the whole thing from resource assessment to actually developing the kit to think about networks and economics and policy as well. and we get our money mostly from European and from UK research councils. So we don't do a lot of stuff directly with industry. It's mostly the sort of slightly earlier academic stuff. Although we are, as I'll now present some things, we're doing more and more stuff with industry now. And my focus in all of this is basically the intersection between the markets and the physical systems, physical networks especially. So engineers are very good at modeling how, for instance, electricity networks work or gas networks. But then what I want to do is see if we could put a market layer on top of that, see how things would work in a market, or how we can design a market in such a way that we can use the physical engineering systems most efficiently. So, so this is why I don't really like the title. I don't really like the word modeling in the title of anything, because I think we should be working on models that the modeling isn't the point. The point is, unless you're a mathematician, maybe. But definitely the point of what I'm doing is trying to actually say something about what would happen in the real world. So the modeling is something, is a tool. It's not the purpose in itself. So this is a very famous quote from a British statistician in the 1970s. That all models are wrong, but some models are useful. And so we can never make models that are, especially if we're talking about markets, we can never make models that are realistic in the sense that they capture everything that goes on in the real world, but we can maybe do something that's useful. And I'm going to present 4 things that I think might be useful. Here's the first. Here's the first one. So the issue here is transmission pricing. So I don't know if you're familiar with how electricity markets. Are you a little bit familiar with how electricity markets work? A little bit. So obviously, if you buy and sell electricity, you have to pay for it. So if you generate electricity, you get paid for that, and how much money you get might depend on where you are in the network, etc., as how much demand there is. But in most markets, you also just pay for access to the network. So there's a system operator which owns and operates the network, which has costs. So it has the sunk cost of the lines that it's already built. It needs to do some maintenance. So there's usually a separate charge which is levied on consumers or producers of electricity or both, just to have access to the network. Now, various markets have various ways of doing that, but usually this is charged mostly to consumers. In the UK, about 70% of the system operators' costs are recovered from consumers, and consumers in this sense means wholesale consumers. So this is utilities who buy electricity in the market. So they pay for the electricity, but they also pay for access to the transmission network. There's some markets where these charges, and obviously if you consume more electricity, you pay more because you make more use of the network. So how much money you pay depends on how much you use. Some countries use your average consumption over a year, or your total consumption over a year, which is kind of the same thing. So at the end of the year, you build for your use of the network based on how much electricity you've used. So that's one approach. There's another approach which calculates the charges based on the maximum consumption that you've ever at any point in time used. And the rationale behind that is it's not really your average consumption that matters, it's the maximum, because the network is essentially built for maximum power flows. And we need to start extending the network when these maximum power flows becomes too high. So it's not really the average that matters, but the maximum. So you charge utilities. You look at what utilities have bought in electricity over the year, and you pick the hour in which they had the largest demand, and then you charge them based on that. Or you can do a third thing, which so the second thing is what Germany does, and most of Europe. The first one also, some European countries use that. The third thing you can do is you can say, well, actually, it's not individual consumers' maximum demand that matters. The network is most highly stressed when the total system demand is the highest. So that's what we want to base the charges on. So this is what the UK does. So you look at the whole past year. You determine in which hour the total system demand was the highest. So this is the moment when the network was most highly stressed. And then in that hour, you figure out what the demand of each of the individual consumers was, so how much they contributed to that system peak, and then you charge them based on that, which isn't the same as the second option where you charge people based on their own peak, not on the system peak. So in the UK, these charges have gone up a lot, and they amount to quite a large fraction of a utility's cost. And just in the last year, they've almost doubled, because running the network is becoming more and more expensive. Especially because we have more renewables and because the network is starting to get old.
So the charge consumer here sort of a proactive way, so they look last year and then.
So the charges are published at the beginning of the year. Like this is what you pay per megawatt or something, but they're only determined at the end of the year, because only then do you know what the highest hour was and what everybody has consumed. So if you're a utility, you know at the beginning of the year you know exactly. So for instance, if it's based on your maximum consumption, you know that you're going to pay £50 per kilowatt of consumption in the hour in which you have the maximum consumption, but you don't know when that hour will be. That makes sense?
If I know when the peak period will be produced and I don't consume electricity in that moment,
you don't pay anything. Yeah, so that's part of the point of doing. So I'm going to explain it later, but that's exactly right. So anyway, so this has been controversial in the UK. It's been controversial in a couple of other countries because these charges keep going up. So there's a question as to, which of these three things do you actually want to use? Is there one which is obviously better and which leads to totally different results? So the question is, which method is best? The UK method, which is charging everybody based on how much they contributed to the system peak, is supposed to, one of the reasons they're doing that is to actually reduce the system peak. So they're hoping that people will do what you were suggesting, is people think, well, maybe the next hour, the demand's very high, maybe the next hour is going to be a system peak, so in order to avoid these charges, we're going to reduce our demand. Of course, as a utility, you can't make it zero, because you have consumers you need to serve, but maybe you can do some things. Maybe you can turn on some diesel generators that in hospitals that must run once a week anyway. You might as well run them in that hour. Maybe you have some interruptible contracts with some of your end users that you can use. So you can maybe have some batteries. So you can do some things to reduce the demand, and that's kind of the point of this whole charging mechanism, is hoping that that happens, and then it will take longer before we have to build more transmission lines, so it will reduce costs for everybody. But still a question now, which does this actually work, and which method is best? And it's important to consider two things. First of all, there's uncertainty about which, so you never know for sure whether the next period is going to be peak. You might have an idea, but your end user demand isn't. Your own end user demand isn't known to you exactly. You don't know what other consumers are going to do. So you can maybe calculate the probability that the next period is going to be a peak, but you never know when it is exactly. You might know when it's definitely not. Like, it's not going to be in summer in the UK. It's going to be in winter, and it's going to be at 5 o'clock. But you're never sure when exactly it's going to happen. But there's another thing. There are also strategic interactions between consumers. So if you're a very large consumer, for instance, if everybody thinks that the next period might be the period in which they're going to be charged, it will probably not be the period in which everybody's charged, because everybody's going to reduce the demand, and it's not. So even if you're sure, but someone else, some other large consumer thinks, actually, I'm going to reduce my demand, it might not be. So there's interactions between the players as well, and definitely in the UK, there's a whole industry around this. So there are at least 20 different consultancy companies which you can pay a great deal of money to advise you on when to use your batteries or something, or when to reduce demand. So there's an enormous industry around this, so which to me means that these strategic interactions and these things are quite important.
The peak might just shift, right? Everybody starts trying to avoid that time.
Yeah.
Maybe every 5
Yeah.
We have some of those companies here too as well.
Yeah. So there's clearly some things going on. So I wanted to come up with a simple way of, this is the only slide with equations, with a simple way of modeling this, and just trying to figure out some of the things that might be going on, rather than, not actually for figuring out what exactly is going on, but trying to do some work to see which of these different charging, whether this charging method actually works, or whether it's just better to charge everyone for their average consumption, because then there's no interactions, and there's no uncertainty. So what if the demand of every consumer has a deterministic component, which I think I've got D, capital D. So you know something about your demand. It's not completely stochastic. You know it's higher in winter. So it has a deterministic component. Then this R thing. So in this time periods, and so N, T is time periods, and N is consumers. So then you can do something which I've called R. So you can reduce your demand, or you might be able to increase it, which you might want to do in some cases. So this is like using your batteries or your diesels or whatever, or maybe some actual demand reduction. actual demand reduction is very rare in the UK. So we have quite a lot of demand side management things, but it's mostly diesel generators. It's 80% diesel generators. Only 20% is actual demand reduction. But anyway, I'm not concerned with that. And then this guy thing is that there's a demand has a stochastic component as well. I know something about it. I can reduce it or increase it, but there's some error. I won't know exactly what's going to happen. And for convenience, I'm going to assume that we know what the distribution of that is. So this is not a one-shot game. We've been doing this for years. We kind of know what the uncertainty around our demand estimates is. And you can plug in your favorite distribution. For here, I'm going to assume an extreme value distribution because it allows me to do some to get some closed forms for things. But you can do this numerically with any distribution, with the empirical past distribution or something. So if you use an extreme value distribution, you can then come up with a closed form for the probability that a probability that the next period is going to be so in this case, the probability that the next period is going to be the peak period of this particular consumer. You can also come up with a closed form for probability that the next period is going to be the system peak. Obviously, that thing depends on the deterministic components of demand. It depends on what everybody's going to do, and some parameters of the distribution. But it's a fairly straightforward expression. And then, so then you can plug it into people's profit function. You can and say that everybody's trying to minimize the charges they pay, essentially, by using this demand reduction variable, by using this R, by using the batteries or the diesels. So everybody's trying to minimize the amount they pay, not knowing exactly which period is going to be the peak, and knowing that there's other people who are going to influence which period is going to be the peak. So with this extreme value distribution, you can get closed forms for everything. If you do another distribution, you might not. I'm going to stick with the extreme value distribution for the purpose of this talk. So you can because you have closed forms, you can do some analytical results. So for instance, if the cost of demand reductions are the same for everybody, so everybody has access to the same technology, everybody has the same diesels, then the three charging methods that I've talked about, they basically bring in the same revenue for the system operator. So if the system operator just cares about revenue, it wouldn't care. If there are differences in costs, that's not necessarily the case, but you can figure out what the differences in revenue are. Let's see, what else do we have? So the system peak charging, so the UK method, which is aimed at reducing the system peak, it does actually work. It does reduce the system peak more than the other charges, but only if the consumers have their own end-user demand peaks at the same time. So if all of the consumers in your electricity markets are utilities, they probably all have peaks around 5 o'clock, because that's when they need to actually send the electricity to their end users. So if that's the case, then the system peak charging everybody for the contribution to the system peak is probably works quite well. And also, if there's more uncertainty about what demand is going to be, obviously all of these charging methods are going to be less useful in doing anything, which is kind of straightforward. So you can do some analytical things, and then you can do some numerical things, and you probably can't see very well what's on the pictures, but it doesn't matter. So there's different time periods, and the very faint lines are its demand, total demand as a function of the charge. But one of the interesting things is if the end user demand peaks are not coincidental. So if you have some utilities, but you also have some industrial consumers who don't have their peak at 5 o'clock, they probably have their demand peak somewhere at 9 o'clock in the morning or something. Or if they're an aluminium smelter, they might not have demand peak at all. It might just be a flat line and then drops off and then zero. Then these strategic interactions start to really screw up your charging method. So if you have different types of consumers in your market, this system peak charging can actually be counterproductive. If you have some weird non-convexities in your cost functions, it might even increase demand. So imagine, for instance, if you're a utility and you think that the next period is going to be a system peak, but your demand is actually at the moment is very low. So maybe you're an industrial consumer or something. So your demand is very low, so you would actually quite like to be charged in the next period. So what would you do? You would increase your consumption just to make it more likely that the next period is going to be a system peak. So this is one of the strategic interactions that can really screw up things. this is probably, the UK is quite uniform in that there are many, the utilities are all more or less of the same size, in which case the charging mechanism works quite well. If you're talking about a country like Germany, which is geographically a lot larger, so the different parts of the country would, or a country like Chile indeed, where the demand peaks are different times of the day, and the demand profiles are different. You probably don't want to use a charging method like this. You want to use a charging method that's based on your own peaks or based on some average. So if you can actually see the line, so there's 3 different charging mechanisms. There's charging based on average. This is 1, 2, and 3 basically. Charging based on your average consumption, based on your own peak, and based on the system peak. There's 6 different time periods that I've plotted here, and obviously you can vary the charge. So all of them give, in this case, all of them give the system operator the same revenue. Obviously, if you increase the charge, people are going to make more deeper cuts to their demand. And if the charge is 0, nobody's going to bother doing anything. If the charge is very high, you have much more incentive to reduce your demand, and you might even do it if there's a very small possibility that the next period is going to be a peak. So I've got 6 time period. This is actually the time period with, if nobody's doing anything, this time period would have the highest demand. Of 42 megawatts, and this is the lowest one if nobody does anything. Nobody does anything, you'd have about 30 gigawatts demand. Obviously, as you increase the charge, all the 3 charging mechanisms are going to reduce demand, especially in the peak. In the lower period, there might be some increased demand, so you have some shifting from the peak to an off-peak period. So, for instance, here we have a situation where the system peak charging actually reduces demand. It's always, you can't really see these lines very well. I should have had a larger picture. System peak pricing is always leads to deeper cuts in demand. But if you look at heterogeneous consumers, it's the other way around. I think I might have that picture on the next slide. Oh no, this is actually, so this is the case with heterogeneous consumers, and the own peak pricing scheme leads always, independent of the charge, always leads to a higher cut in the peak than any other pricing mechanism. But the picture is not important. The important thing is strategic interactions start to matter if you have heterogeneous consumers. This is one way to model it. It's a way that works in that you can get nice solutions that you can play with, so you can get some answers that are quite generally true. And that's probably all I want to say about that. So what I like about that, so we have a real-world situation. It's impossible to model all the complexities of this and what all the consultants are doing. Even they don't know. But you can have a quite simple model which shows you some of the features and can give some indications in which cases one policy might be better over the other. And obviously, if you bring this to policymakers, you don't tell them anything about the model because they don't understand anything that has an equation in it. But you can explain some of the rationale behind it even without the equations. So here's another example. So this is work I'm doing with one of my PhD students and with a colleague from the mathematics department and with electricity markets and regulatory consultants who work for Nigerian distribution system operators. So Nigeria is really fascinating. If you ever want to do something really fun in electricity markets, and do something with a real developing country, because things are really strange in Nigeria. But the reason Nigeria is especially different is so there's constant, as most developing countries, there's constant load shedding. So there's not enough generation to cover demand at any time. So your problem isn't how do I meet demand. Your problem is how do I shed the minimum amount of load. So it's not optimal power flow, it's minimum load shedding. And you don't care about the cost essentially. You want to use all the generation capacity that you have as much as possible. So they do actually, in the Nigerian control room, they have a figure on top which is the demand, and then everybody just completely ignore that. And then there's a line about what part of demand is actually served, and that's what you care about. The demand is completely fictitious. So in fact, we don't even know what demand is because it's never served. There's been some research, and we're doing some research in that. it's kind of an important thing to know, especially if you're thinking about investing in new parts of the network. So we're also doing some modeling on that. Is how can you actually how can you do that if you don't know what demand is? So there's now a questionnaire which is now live in Nigeria to ask people what kind of appliances they have in the house and how the house is insulated, so we can try and infer that. But anyway, this is different. So it's constant load shedding. The network's highly stressed. So there's voltage problems pretty much everywhere, at every level. So it's not just generation, it's also the network that's constraining what you can actually do. And the available generation capacity is very, very variable. So in a normal country, you would expect the available generation capacity to be more or less a flat line. And then someone builds a new power plant, and then it's a little bit higher. Maybe if you have some wind, the available generation capacity is a little bit variable, but basically it's the same. Not in Nigeria. The available generation capacity can go from 20 gigawatts to 10 gigawatts in an hour. Because the plants are not maintained very well, they can go offline suddenly, and especially because of gas availability. Someone blows up a pipeline somewhere. Actually, people don't blow up gas pipelines. People try to take oil from pipelines, but then if they get the wrong one, they blow up gas pipelines. So the available generation capacity is very variable. So so there's a question about how can we do any modeling in this? But what we're mainly interested in is what's the best policy for shedding load? We're going to have to do it, and the government should, and the regulator should have an interest in this. So we can either just try and serve as much consumers as possible, which probably means we will just serve the consumers that are in the cities, in the central area of Nigeria, and the periphery will just get nothing.
Where does the energy mostly come from? Oil?
It's mostly gas-fired generators, because they pump the oil industry. Actually, I might have a picture. So this is Nigeria. This is where most of the electricity. So this is the network, high voltage network. This is where most of the demand is, and almost all of the generation capacity is, which is gas fired. So in the north is where the oil is actually produced. Gas is mostly a byproduct of oil. It's mostly flared, actually, and just burned there. But some of it's piped down there, and then there's gas-fired generators. There's some oil-fired generators as well, but it's mostly gas. And there's some hydro as well in the north, I think. But anyway, so if you just minimize, if you're an engineer and you just minimize the load shed, you say I want to serve as many consumers as possible. You serve this region, so Abuja is the capital city. So you basically serve this region, and the people living out in the periphery get nothing because it's there's losses on these lines and there's almost no generation capacity there, so you wouldn't bother. Obviously, as a regulator, that's maybe not what you want. Maybe you want to have a fairer policy and make sure that the people in the periphery have the same access to electricity as the people who just happen to live closer to the city, because there's actually a lot of people living up there. So the question is, how can we trade these two off, and can we actually give policymakers a cost of having a fairer policy? So what we've done. So first of all, the question is how can we model this? And so we have a network model which is pretty large, which actually has more or less the whole network. There's another thing about Nigeria is that we don't really always know what the network looks like. Slightly more worrying is that the system operator doesn't quite know which lines actually exist. So we have a map from there, and some lines are dotted. So we thought maybe these are lines that are under construction, but they're lines that they don't exactly know whether they're there or not. Someone might have taken them or whatever. But anyway, we have a network model which has been calibrated, and we're pretty sure actually works, which has all high voltage links in there. The main objective is to minimize load shed, so it's not optimal. It's not the optimal dispatch. We want to dispatch as much, so we don't care about cost. Essentially, we just want to minimize load shed. And it's quite, this is one of these cases where the simplest possible model doesn't work. So you can do a DC approximation and linearize everything, and that doesn't work in this case because the network is so highly stressed. So I said that available generation capacity was highly variable, so we have a couple of scenarios for it to. So these are actually real values, so it varies from sort of 3 gigawatts to 7 gigawatts, can vary hour by hour. This is if we just minimize the load shed, so we decide which consumers to serve to maximize the number of consumers that we serve. This is what a DC model would say we can do, and this is what an AC model would say we can do. Now, especially if we're sort of into higher generation availability, the difference between these numbers is pretty large. because so it's not only generation that's constraining, it's transmission, and especially there are voltage problems that mean that we can't actually, the things that the simple linear model predicts, we can't actually do in real life. So the simplest possible model doesn't work, so we need an AC model to do this. So that's the first lesson. And then the second thing is, so if we do this, if we just minimize the load shed and we get those figures on the previous slide, the remote regions, as I said, essentially get very little power. So Nigerian government has a policy of fixed load allocations. So they say that, for instance, this region in the upper northwest Jos has to get 15% of all electricity produced over the course of a year. So the Nigerian government clearly thinks that this, just minimizing the load shed and sending all the power to the cities is not what it wants to do. It wants 15% of the power to go to the north as well, and it wants to get 10% of the power somewhere else. What we can do is we can impose those fixed load allocation targets on the load shedding problem, and say, okay, if we follow the policy rigorously, what's going to happen? So obviously that depends again on what the generation availability is. So we have a couple of lines for all the generation availability scenarios. So this is what if 3 gigawatts is available, what if 3,500, etc. up till this line is the highest generation availability. So top of the line is essentially we just ignore the government's policy and we do minimum load shed. Bottom is we stick to the policy rigorously, and we make sure that 15% is going to Jos and 13% is going to the other region, etc. And then we also look at so what if we can deviate from the policy a little bit? So what if in total we can deviate 50 megawatts on average? What if we can deviate 200, etc.? So this is strict policy. This is essentially no policy at all, and this is somewhere in between. And on the horizontal axis is the load supplied. So if we don't care about the policy at all, if we have 3,000 megawatts of available generation capacity, we can serve just a little bit under that. If we have this is 7,000 megawatts of generation capacity, we can serve about 5 gigawatts of load. But especially in these higher generation capacity, as we start sticking more and more rigorously to the policy, we are actually serving less load. So there's a cost to this policy, which, for instance, if in this highest generation capacity, the cost of the policy is basically, it's almost a gigawatt that we generate less, that we serve less because we're sticking to the policy. So the reason for this is we have more losses because we're sending power to remote regions. We might create some transmission constraints, which means we can't use certain power plants. And in the very extreme, we might have to scale everybody down. If we really can't get more power somewhere, but we still need them to get 15%, we just give everybody else less. That works. So there's a cost to this policy, and we can quantify this cost in the number of megawatts or in the number of megawatt hours over the course of a year that we miss out because we want a fairer policy. That's not to mean this policy is bad. It's just there's a cost. Yes?
Do you think that the value of load flow is homogeneous across all?
Yes. So we essentially don't know we have no data about this. So we're assuming that serving a consumer in a remote region is the same as serving a consumer in another region. We're doing some more work to try and differentiate this, because this also assumes that it doesn't matter. This is just a one-time period model. Of course, in the real world, it might not be so bad if you have less electricity if you know at least when it's coming. So we should really have a dynamic model, which we're working on. But yeah, you're right. I mean, there might be a higher value to load in the cities.
If you have those numbers, then the policy would be implicit on those values, right?
Yeah. But I think that's a number we're never going to have. I think the Nigerian government will probably say, if you ask them, yes, it's the same. The value of lost load is the same everywhere, because they can't say it's higher in this region than another. Yeah, but it's not in the questionnaire that's going around. We're also trying to figure out, because basically the value of lost load is reasonably straightforward in Nigeria, because if people don't have electricity, they'll just turn on the diesel generators. So if we know, but they reduce their demand as well. Like they turn off the air conditioning and then they use the diesel generator to run the fridge. So in the questionnaire, from the questionnaire, we'll have some data about how much people reduce their demand and how much diesel they use, and we know what the price of diesel is. So we can come up with some estimates. So eventually we might be able to do this. So this is a rough approximation, but this is, current policy is costing you, between 0 and 1 gigawatts, depending on your generation availability in load that you can observe in any moment in time. And we can convert that, because we know how often these scenarios occur, we can convert that into a megawatt hour number, which I told the student to do, but he hasn't done it yet. So the current policy comes at a cost. So this 1 gigawatt is not a lot in sort of Western standard, but it's about a quarter of the supply reduction in worst case. And we're doing some more modeling to figure out, especially some dynamic modeling, to figure out if we can at least have sort of blocks of hours in which people are served. Maybe that would reduce some problems. There's another thing, is that we've also looked at investment in the network, because this is obviously a situation that screams for more transmission. So the Nigerian government has essentially no money, so we thought, what if we just install voltage support in crucial locations? Maybe then at least we can use all the generation capacity we have. If the network is not, since the voltage constraints are the most binding constraints. And we can do that. So we figured out that you can, if you only in a few places you have to install voltage support, and you can dramatically increase supply. So we thought it's a good policy conclusion, do it. But then we talked to the distribution system operators, and it turns out that, so because of this constant load shed, the transmission system operator tells the distribution system operators, who are physically integrated, so they also serve the consumers, it tells them how much power they're allowed to draw. And it has essentially no instrument to make sure that the distribution system operators do that. So currently, because there are so many voltage problems, the distribution system operators stick to it, because if they draw more power than they're allocated, the voltage will go down, and part of their load is voltage dependent, so they get less money. If we fix all the voltage problems, the distribution system operators can just draw more power, and we'll get frequency problems. So the current bad state of the network is making sure that everybody does what they're supposed to do. If we fix something, if we think that we can fix some things easily, cheaply, we might create different incentives for market participants to do things that they're not supposed to do. So we have an equilibrium version of the same model, and we're working on that. So far, we're not seeing a lot of that. So we might be all right with installing more voltage support, but again, it shows that you can't really decouple the engineering. You can solve an engineering problem, but it can create problems in the market that you haven't thought of. So that's also ongoing work. So do I want to? Yeah, I'll do this quickly. So this is another project together with a postdoc, James Robertson, and a colleague of mine from the Institute for Energy Systems as well. This is very recent work, so I don't have any results for this. I just wanted to say this is another thing that we're doing. So the project is about, essentially, is the value of storage. What's the value of storage to owners, to the system, depending on where it is, whether it's really big things at transmission level or really small things at distribution level or in people's homes even. And maybe what's the impact of storage as well to other market participants. So if you're a gas-fired power plant, storage could either help you, because you might be able to run at a constant level rather than having to ramp up and down all the time, so you can be more efficient, or it could kill you, because if you're a peaker plant, maybe you're not necessary anymore if there's storage. So these kinds of things we want to look at. And so this is UK. Well, it's UK and European-based work. So we have 29 bus UK network model. For this, we have a rolling horizon. So it's not a perfect foresight optimization model, but it's a rolling horizon model to try and capture some of the uncertainty that there is in around optimizing how you use storage. So you optimize 48 hours ahead of time, but then you sort of take one step further in the next hour, and you get some more information, and you do the whole 48 hours again. And then you do another step and you do the whole 48 hours again. So you never see the complete picture, you re-optimize all the time, which is kind of what happens in it helps us doing the modeling, because we can do larger models and we don't have to do enormous stochastic models, but it's also kind of what happens in the real world is you have information about things like rainfall, you have reliable information about things like rainfall for the next 48 hours. After that, it starts to become very, very uncertain. So you re-optimize all the time. And we're looking at 3 types of storage. One type of storage, which is sort of transmission connected storage, so it's like a generator. It's there and it can be dispatched. There's non-dispatchable storage, which is visible to the system operator, so it knows it's storage, it knows it's there, and we kind of know what it's doing. So this is distribution connected storage. We know that they try to make money by maybe playing on price differences, but we can't control it in a way that we can control large power plants. And then there's non-dispatchable and invisible storage, which is like your Tesla Powerwall in your home. We don't even know it's there. So the only reason that the system operator sees it is because it sees that demand patterns have changed slightly. It doesn't know whether that's because of storage or because people have just changed the demand patterns. So 3 different types of storage, and in that model, and just now at the moment we're running that and seeing if what the values to the system are, or maybe because the second and third storage options might even be bad for the system, so it might actually increase system costs if people use the storage for things that are good for them but not optimal for the system. And we seem to be seeing some of that happening. Is that if there's a lot of storage in the system, but it's just used by consumers to reduce their electricity bills, it might be bad for the system as a whole. And then together with University College London and the University of Strathclyde, we have a European model with investment, and we sort of run the 2 models soft-linked. So we can run a European model which says, okay, we need to invest in all these things and in these interconnectors, and then we can go to a UK model, run that, and see what the implications of that would be for the UK. So we can also trade off interconnection capacity and storage, for instance. So if we have more interconnection capacity with Europe, you think that the value of storage is lower in the UK, which has a policy conclusion attached to it as well, is that if we go for both, we have to make sure that the storage, and we want the private sector to build the storage, we have to make sure it's still profitable if we decide to go for more interconnection capacity as well. So this all goes in AIM. So we have a network model and we can visualize everything. So this is the model, and we can visualize where generation is happening and what's happening to the storage, for instance. So here are a couple of storage profiles over the course of a day. I think on top is demand, so it's demand with and without storage. And then this is for there's different types of storage plants. I think this is probably quite a small one. This is a bigger one over the course of 1, 2, 3, 4 over the course of a week. I mean, just to kind of illustrate what the model looks like if you actually use it. So this is fairly these models are fairly usable. Is that if anyone's interested in that, we can show you, and they're reasonably intuitive even if you don't do programming. You can just change some parameters and see what happens. And then finally, of course, I have to mention some of this. So this is some work I'm doing with Francisco and some other people. And the question here is, so we know how to do, we've all done this transmission planning thing. We can build big models that decide where to build new lines. We can make them stochastic, because we don't know exactly what happens in the future. But if you make them stochastic, what everybody definitely in the sort of techno-economic community does is we assume that people are risk neutral. So they just maximize their expected profits. In the real world, nobody's risk neutral, and people care a lot more about avoiding the worst outcome than the average one. So the question we're asking for this particular paper is, we've been ignoring this. Have we made a really big mistake by doing that? So is our optimal transmission expansion plan, for instance, going to be a lot different if we're risk averse, or if the generators who build generation capacity to connect to the network are risk averse? So to do that, so Francisco has a 240 bars representation of the western interconnection, so the western part of the. You might have seen some of. Have you presented this here? You have. Okay, so you will have seen this. Some of you will have seen this. So it's the western part of the US. It's a pretty big network. So this is a simplified version of it. We're saying that first there's a transmission system operator which decides where to build new lines. Doing that changes prices for electricity. So once you've done that, generators will locate in different places. Like if you build lots of transmission to one place, to a place where there's good renewables, then maybe people will actually build generation there. So you have to take that into account. So you do your transmission plan, but knowing that if you change something, you are going to change incentives for what generators are going to locate. And there's two types of transmission investment. There's backbones, sort of reinforcing the backbones of the network, or you can connect to new places where there are good renewable resources. And then, of course, since I'm an economist, I can make assumptions on things. If we make some assumptions, we can actually, this bi-level thing, we can collapse that into one and solve it as one optimization model, which will have an equivalent solution to the bi-level problem. So we have to assume that markets are perfectly competitive, so no one can influence prices. And we have to assume that risk can be traded as well. So you can insure yourself against things happening. Now, in the real world, there's not quite perfect competition. There is some market power, but regulators try to avoid that. And there is not perfect risk trading, but there's quite a lot of risk trading. If you're a generator and you're afraid that something's going to happen in the future, which is just going to affect your profits, you can try and insure yourself against that.
So you're saying that the generator and the generation and transmission have the same attitudes.
But they have the same attitude to risk. Okay. Yes. We're working on a different version where the transmission system operator might be risk neutral and generator risk averse, or the generator might be more risk averse. But that turns out there's some of that on the board, but it turns out to be really complicated. So we're saying that both, in this case, both are risk averse. So there's a risk averse transmission planner who builds new lines, anticipating what risk averse generators are going to do, and a transmission operator maximizes social welfare. Whereas so it's kind of the policy, it's kind of the regulator. Whereas the generators maximize their profits. I mean, obviously, it's a very simplified representation of what actually happens, but it allows us to tease out some of the effects of risk aversion at least. So this is what the network looks like. It's not very interesting. I thought when we started doing this, I thought this was a very big network, and then my student said, "Oh, I have the 640 bus version of the Nigerian network." So we try, so this is an engineering model, but we try to have some market details. So we have, so we use CFAR's conditional values at risk to quantify the risk. So generators are not maximizing their profits; they're maximizing a weighted average of their expected profits plus the CFAR of the profit, which is essentially putting a higher weight on the worst case scenarios. So you maximize a weighted average of your profits in different scenarios, but putting a higher weight on the worst ones. But of course, before you do this, you don't know what the worst ones are going to be, but you want to avoid the worst solutions. And there's things like renewable targets, and there's obviously limits on in the transmission network. So what we're seeing is that if people are more risk averse, there's a bit more generation investment. People tend to build more renewables, because the renewables are sort of an insurance against future things happening, like high fuel prices. Because the renewables are, it's like an insurance contract. It's something very expensive that you buy, and then you're not really exposed to. Then it's really cheap to use, and you're not exposed to fuel price risk. Also, some of our scenarios have high renewable targets, and to insure yourself against that, renewables also work. We're seeing a bit less transmission because generation and transmission are substitutes to an extent. But more interconnections to renewable hubs because the transmission system operator, anticipating this higher interest in renewables, is building those lines. But all these effects are quite small on a total level. They can be big in individual regions, but they're quite small on a total level. There's various reasons for that. One reason is that you can do some small things in these networks that already reduce your risk a lot. There are some risks that you just can't do anything about. So if there's a risk that in the future there's a very there's a very high renewable target that the government sets, you're just going to have to build those renewables. There's very little you can do to insure yourself against that happening. So it's going to be an expensive world.
Just a quick question. Curious about the first. So there's more generation of renewables.
You build more if you're more risk averse. If the world is more risk averse, there's more investment in renewables.
There's more volatility.
Well, obviously it depends what your uncertainty is, but in our case, some of the uncertainty is about fuel prices. So as I said, once you've built renewables, you don't care about high fuel prices anymore. So if you're really worried about fuel prices being high in the future, renewables are one way to insure yourself. The other thing is if you think there's going to be a very strong renewables target. So individual states, for instance, might have targets for 20% renewables, 25% renewables. And if you don't have them, you have to pay a penalty. So again, to insure yourself, you build more renewables. And there's some anecdotal evidence in talking to people who actually do this planning. There are people who have said, no, we're actually considering investing in renewables, not because we care about the climate, but because we're afraid of fuel prices being high in the future. So there's some evidence that this actually happens. So anyway, but these changes are quite small. But then if we look at local effects, so there's some bar charts here, which is the change. This is generation investment, this is transmission investment in individual states relative to the risk-neutral case, as we put a higher weight on the worst scenario. So the white bar, we only care about the worst scenario, and the things, the sort of black bar, we care a little bit more about the worst scenarios than about others, etc. So in some states, so like Arizona, we're very risk averse. We built, 4 gigawatts more, which is 4 big power plants, which is very considerable. In some states like California, we don't really do anything because they already have so many renewables that they're basically already hedged against future things happening. This is the places where there are good renewable resources, so this is why we built more. We built some more transmission in those places as well. In most other places, we build less transmission if we're more risk averse because there's more generation, so we don't need to import so much power from other places. In California, for instance, we do build more transmission capacity because California has very good renewable resources. So if we have the transmission capacity, we can use that in other states, just in case there's a high renewable target in neighboring states. So even though differences are very small, if you look on average, there's maybe 0.1% more generation, to individual states this matters. So to policymakers in the state, they care about having another 4 gigawatts of generation capacity. So risk aversion matters not necessarily if you look at if you're the U.S. government and you look at big things happening, but it does change where you put things quite a lot. So it'll be decision makers in local government that will care about this. So if we do modeling, we have to make sure that especially if we're being asked questions by these local decision makers, we have to account for these kinds of things. And so it's also, these are just 4 projects that I'm involved in. I do other things as well. I do some things on transportation as well, especially how transport networks and electricity networks interact. We have a very new, announced last week, Center for Energy Systems Integration, which is going to work on linking models. So we have all these different models I've presented before. The real world is a sort of very complex interaction between all of these different sectors. How can we do something with that? And all of them are. The world is highly uncertain. Many of the models are deterministic. Do we actually know what models tell us? And examining interactions not just between energy, but also interactions with heat and transportation. So in Scotland, for instance, heat starting to become very important if we want to be carbon neutral in 2050, which is what the Scottish government wants. We need to stop burning gas in our houses as well. So we need to get the heat from somewhere else. Electricity is probably not, in Scotland, is not the most efficient way to do it. So can we use waste heat? I'm doing some modeling on that as well. Postdoc's doing some modeling on that for the Scottish government. Big data is increasingly a thing in the UK that there's lots of money for. So I'm doing some work with. There's a new thing called the Alan Turing Institute, which is a new big UK institute for data science, which has hundreds of millions of funding. And how we can use data to do these, the kinds of models that I've presented. Can we make them better if we have more data? And at some point we can't, because the optimization methods we use can't deal with that anymore. So maybe we have to do something else. So if we do a simple transmission planning exercise, so currently we're using maybe a year of demand data and a year of wind data at half-hourly level. What if we have readings from individual houses for every minute? So we have petabytes of data. Which bits are valuable, and which bits should we put into our models, and which bits should we not care about? Then I have a new student who is working with EDF on one of these questions. So they're concerned about when should we do maintenance on our plants, especially offshore wind. So it is quite expensive. You need to actually go there in a boat and do some things. How can we use, especially real-time data coming from the electricity system and from the market as well, to make that more efficient? So historically, people have used past data about wind turbines, like what's the probability that they fail once they've been running for so many years. But you also want to know what's the price going to be in the next period, because I don't want to take my wind turbine off if the price is going to be very high, even if I know that I need to do something about it quite soon. I might wait until the price is lower again, so I'm not losing as many profits. So that's me, and if you're interested in any of these things, then please come and talk to me. I'm happy to collaborate with. I'm being told by my University of Warsaw said I need to collaborate with people in Chile. So Chile, unfortunately for me, but fortunately for you, is graduating next year from a higher middle income country to a high income country, which means that we can't get funding from developmental sources anymore. But the University of Edinburgh has decided that Chile is important. We're getting more and more students from Chile as well. So there's clearly opportunities for collaboration. So come and talk to me. Thank you.